Hello everyone, I'm Babak Tehranirad, and along with my colleague Herdman, we're going to introduce Hydrocosmos Coastal Forecast System for the San Francisco Bay Area in this presentation. As Rob Cifelli mentioned in the previous presentation, this model is part of the AQPI project. This model is built with the Delft 3D Flexible Mesh model suite and uses a combination of 1D and 2D grid system to capture water levels within the San Francisco Bay Area. The 1D grid cells are mainly used to capture the river system in the San Francisco Bay Delta and also tidal channels and other small tributaries within the San Francisco Bay to improve the efficiency and the physics of the model. This forecast system is coupled on the offshore boundaries to a global water level forecast system, HICOM, to import the remote non-tidal residuals. It's also coupled on the discharge boundaries to National Water Model and uses the forecast data from National Water Model. And also on the for the surface, we're using the atmospheric inputs from her forecast system and capturing surface mean sea level pressure and wind velocities to simulate water levels within the San Francisco Bay. We have performed several case studies using this model. One of those case studies was focused on identifying the role of discharges and remote non-tidal residuals on capturing and forecasting water levels within the San Francisco Bay Area. And it was shown for the storm of February 2019 that remote non-tidal residuals, which are imported from HICOM, and discharges, which are imported from National Water Model, can contribute to about 10 to 25 centimeters of extreme water levels. So that showed that these models are a very significant part of a forecast system, and we need to have them as part of our coastal forecast system. The operational system right now runs every hour and produces 19 hours of forecast. And as you see in this picture, the model results are with an acceptable level of 10 centimeter error margin, and it's running very smoothly. And we hope that we have this model out by the end of 2021. The initial goal of this model is to provide users with time of first flood, flood duration, the time of peak flood, and also flood potential from wave runup. And as you see, products like water level for the entire San Francisco Bay and the inundation zone, and showing the infrastructure that could be inundated and flooded. However, we're using this model in several other applications, which my colleague will dive into in the next slides.
One particular application of this model will be to help with managing releases of the Crystal Springs Reservoir into San Mateo Creek. The managers would like to know the water levels at or near this highway overpass, indicated here in the orange star, to manage reservoir releases in a way that minimizes flooding, as this is a critical part of transportation infrastructure in the area. On the lower left, we see the reservoir which drains into San Mateo Creek on its way to the bay. And this map shows the 1D representation of the channel in red, and again this critical location is shown with the orange star. Usually there are no gauges below the discharge point. However, the reservoir managers had a short-term gauge at the highway crossing of concern for a few months in 2017, allowing us to perform this case study. Using the upstream observed releases, the model predicts water levels well at the place of concern. These hindcasts resulted in a mean error of 4 centimeters and a root mean square error of 14 centimeters. The largest error values that occurred are due to the times when the model discharge from the reservoir reached the observation point slower than it did in real life. This phase lag will be fixed in the next iteration of the model release, so we anticipate the errors only getting smaller. Of course, when running in forecast mode, we won't have the actual upstream discharges. So we wanted to understand how forecast errors will affect the simulations. This is represented by phase lagging and lowering the actual observed discharge values. And we found that errors in the value of the peak discharge are much more important to water levels downstream than errors in phasing of the discharge. In low discharge time periods, such as what happens at the end of this simulation, coastal water levels really dominate that location, and the water level predictions are very good regardless of errors in the discharge. So this accurate prediction of coastal conditions will be very useful to managers attempting to time upstream water level releases to low coastal water levels, and we also anticipate that our model results will only improve as regional improvements to the national water model occur.